more people will see this on video. So we're just going to do this one question. Chapter 6 is, for the most part, just an introduction to convection. So we've done a lot of conduction, and the idea of convection is that we're a little bit less sure about what's happening. Conduction, the molecules all stay together, very nice, but there's a lot of randomness to fluids, as you would have learned in your fluids.
Excuse me, Connor.
Yeah.
Can you go back to the quiz question? I didn't take a screenshot.
Okay, I'll go back for just a couple minutes and then, or a minute or so.
Done. Thank you.
Good? Awesome. Okay. So in a lot of these questions, the strategy will be to look up these kinds of non-dimensional numbers, and then you can solve. You're going to have a bunch of tools depending on the situation, depending on what kind of number you get, you're going to have some tools to solve it. And so that's what this question is like. We have a little bit of information about this plate. We know it's 1 meter long, 3 meters per second, and then we just want to determine the convection heat transfer and the nuisance numbers at various lengths. And we want to evaluate the properties of air at 40 degrees Celsius and 1 atm. And typically, if we don't know this, if we're not given this, we'll use the average between the surface temperature and our infinity number, if we know our surface temperature. Again, it very much depends on the question, how you approach these. So the first thing we're going to do is we're going to look up our properties of air on this table A15, and we'll do it at our temperature of 40 degrees Celsius. And from here, we'll grab, I have them written down here. So we'll grab our thermal conductivity of air, so which is 0.02662 watts per meter Kelvin. Our viscosity of air, 0.702. And our Prandtl's number. So that's given on this chart as well. Our Prandtl's number. This is also something you calculate in some situations. Okay, so first what we'll do, we have a flat plate, and in this chapter we don't learn a lot of the specific cases. That's more in the next chapter, but we do learn one, which is laminar flow over a flat plate. We know how that is related to our Reynolds number, and so what we first want to do is understand if this is laminar flow, and so we do that by calculating our Reynolds number for X, and this is also going to depend on our X, because as we move along this plate, the flow is going to change and eventually it's going to start to become turbulent. So V, our location, and our viscosity, and we're trying to find it specifically at 0.75 meters. And this is equal to 1.32 times 10 to the 5. And so what we say is that if ours is less than 5 times 10 to the 5, then we know that our flow is laminar. And the nice thing about this is, sorry, it took me a second to understand that. So the nice thing about this is we don't need to also check it at 0.5, because this is how flow always develops. It's always going to develop laminar, and then eventually turbulent. So as long as it's still laminar at 0.75, then we also know it is laminar at 0.5, which are the two places we're trying to find our convection coefficient at. So again, this isn't always true, but for a flat plate laminar flow, where our convection coefficient is related to our Prandtl number to the 1/3 k v over viscosity x. So this is velocity and this is viscosity. Oh, this is to the 0.5. So these are both things we know from the question and from the chart. So at our 0.5 meters, this is equal to 0.32, 0.7255 times 1/3, 0.02662. 1.702. And then see if we can just move this over. Actually, I'll go down to the next line. So multiplied by so this will be equal to 4.715 watts per meter squared Kelvin. And then same process for at our 0.75. The only difference is our x value changes to 0.75. So our hx in this case is equal to 3.850 watts per meter squared Kelvin. So you can see actually heat transfer will be going down across the plate. And so this is kind of, I guess, to introduce you to these non-dimensional figures and also introduce you to that this H depends on a lot of things, like the type of flow, the size of the plate, and even how far along you are on the plate. So it's quite a complicated thing, but you'll find that what we have is we have a tool for a whole bunch of different applications, and we'll just apply it, have a certain tool set for a certain application, and we can actually figure it out fairly accurately a lot of the time. So the last part of this question was to find Nusselt's number. So that's going to be our h of x, our x over k. So again, we'll do it for both distances for 0.5. So its number of x is going to be equal to what we calculated in the last one times our x divided by 0.0. This is non-dimensional 88.6. And so for this question, we don't have to do anything about this, but later you'll see different applications for, again, these different non-dimensional numbers. For 0.75, our Nusselt's number is 108.5. And the last thing to just know is that often this is kind of in the discussion part of this question. So in this case, we were only asked to find h at a specific x. And again, h changes over x. And so if we wanted to find, sometimes we'll be asked for the average convection coefficient. And this will be, you integrate, well, it's not how you spell that. Integrate your hx over the entire length. And usually we call that h bar. Okay, so not the most complex question, but just an introduction into this idea that h is something we calculate. We calculate it using a lot of fluid dynamic stuff. And depending on our situation, there's going to be different ways of measuring h.